Record.
I apologize for that. So what I'm going to talk about is, I guess, changes in extremes. My current interests are about changes in extreme rainfall. I have been interested in extreme temperature in the past. And the questions I tend to ask are, how much of human influence has changed the distribution of those extreme events, and how might they change in future? So I'm going to provide two examples relevant to Scotland, one from a paper that's just appeared, which was looking at very short duration rain associated with the Carmont rail crash back in 2020, and then another study looking at changes in temperature extremes after the heat wave that we had in Scotland in 2018 when it reached 30 degrees. My current thinking is broadly that showing that human influences have cooked the planet, as I put it, is societally relevant but scientifically boring. We know the answer. And in fact, I think temperature extremes are also reaching the same point. We keep cooking the planet. It therefore becomes more and more obvious that we're in a different climate. So that's what I'm going to talk about. So in August 12, 2020, which was just after the first COVID lockdown, I was on holiday north of Aberdeen when this huge thunderstorm moved up, basically starting just north of Newcastle, transited over Fife, where it induced some landslides where there hadn't been any for about 100 years, dumping heavy rain as it did. And then the Aberdeen to Glasgow train, after reversing due to potential closure of the line, derailed. It was traveling at speed. It happened near Carmont. And in that disaster, there were 6 people on the train and 3 of them died. If the loadings had been more normal, we would have seen much worse impacts. So here's a picture of this. You can see the sort of trains come to a halt when the carriages have fallen off the bank. The proximate cause of this, and I will say a little side message when I said this, is gravel from an poorly or not to spec drain being washed out by extreme rain onto the track, and that's what caused the derailment, and that's what you can see here. In my darker moments, I think, when I were a young scientist 25 odd years ago, I was looking and working quite hard with colleagues to understand global climate change. And we showed back in 2000 that, as I rather flippantly put it, humans had cooked the planet and continue to cook the planet. And now I think to myself, I'm looking at extreme rain on a drain in Scotland and seeing human influence. I wish I were in an alternative timeline, I sometimes think. Okay, so that's what's interesting. And so the interesting part for me isn't the drain. I'm not an engineer. I have no pretense or desire to become an engineer. But however, I am very, very excited by weather hazards and how might change. So, and this is a short duration. There's no direct rain. There's no rain gauges which measure the rain directly. But we do have radars which are measuring rain in Scotland. It has to be interpreted. I won't say very much about it, but they tell us something. However, we kind of have a scale problem for rain. So this picture might be overcomplicating it. The radar essentially is processed in 2 different ways. So one way is a 5-kilometer area and 15-minute times, and that's what this blue line shows. And then the red line is the 1-kilometer resolution rain over where the drain is draining, the hillside, and shows in 5-minute analysis. The dotted blue line is the cumulative amount. The circles here show roughly where we get 5 minutes. The time of this event is about 4 hours. So the rain starts about 4:30 GMT. Finishes about just after 8, so it's a sort of 4-hour event. The derailment doesn't happen for about an hour after the rain, so it's more a question. I think the track is presumably blocked at some point. The gravel's on the track about from here onwards. The derailment is just the first train to come through. For reasons of comparison with climate models, we're going to turn this into 1-hour data. That's what this shows. And essentially you can see the rain kind of comes in a 3-4 hour burst. And then maybe it's the 1 hour burst at 7 a.m. or 700 that does it. Okay, so that's the sort of observations. We can calculate return values from the radar, involves a bunch of statistical modeling. The main point I want you to get away from this is the 1 hour is actually could range depending a little bit on the resolution. So here's 1 kilometer, here's various 5 kilometers, around about 20 years, but on longer time, on bigger regions, could be somewhere between 15 years and 50 years, so quite uncertain. Similarly, the 4 hourly on the 1 kilometer, it's a bit under 50 years. Actually, on the 5 kilometer, it's between 50 and maybe 150 years. So these are rare events. They're not an event you'd expect to occur every year, far from that. Though you might expect something of this magnitude to occur somewhere in Scotland every year. So that's the sort of observations. And then the Met Office, as part of its climate impacts program, has run an ensemble, so a lot of simulations at very high resolution, 2.4 kilometer resolution. And that's really important. Those are models that are able to represent the processes that occur in thunder, or at least the important processes that occur in thunderstorms. So we would expect their results to be more reliable than the large-scale climate models, which have resolutions of 100 to 200 kilometers for these very short duration, short timescale events. And that's what this is showing. And there's quite a lot on this. I'm going to focus, I think, on this figure, and then I'll wave my arms to the rest, or wave my mouse to the rest. So what is this showing? This is showing the probability ratio between the probability of an event of magnitude on the x-axis or larger. The black line is what happened at Carmont, so say 30 millimeters. And it's saying that in the pre-industrial climate, we have about 100% that would occur maybe every 25, 30 years or so. This blue line is when I was a student in Edinburgh in the 1980s. So 5% increase on pre-industrial. And then the red line here is the future, a world in which the global average is warmed by 2 degrees. To put things in context, at the moment, we are at about 1.3, maybe getting quite close, but maybe up to 1.5 degrees centigrade warming relative to pre-industrial, so some metric of climate change. So in the current world, the 2000s of the Carmont disaster, it's about a 20% increase. So, okay. Another way of thinking, so that's how more frequent they are. So they were 5% more infrequent than they might have been in the late 19th century. For Carmont, about 20%. Into the world of 2 degrees, about 40%. If we look at the change in intensity, that is, if we think about rainfall occurring every, say, the 1 in every 10 year, about 10 summer event, or every 100 summer, we can ask, how is the rain changing the intensity? And that's what this is showing. And essentially, again, depending where you are, it's increased by about, for the Carmont, by about 7.5, well, a little bit when I were a student, about 7.5% now, and then in the warmer future world, about 15%. This is 1 hourly, and that's really all I want to say about that, I think. So then I'm going to talk about changing topics. So what's the takeaway from this? The takeaway from this is that climate change is already affecting things on really quite small scales. So the annual extremes in hourly maximum rainfall, there is, we think, a climate change signal in there. And we have to do more work to essentially demonstrate this properly. Okay, so the other thing is, in 2018, there was a heat wave in Scotland where I think in Glasgow, the temperatures exceeded 30 degrees. And so we asked a question, well, and this is, we probably did the work 6, 7, no, when did we do the work? We probably did the work in 2018, I think, fairly shortly after it happened. These are showing 2 different weather stations, Eskdalemuir, which is here, I think it's the lower one, sorry, it's the light blue, Auchincrave, which is near an old agricultural college near Ayr, in dark blue. Black is the observations averaged over the northern British Isles. And this shows the pressure. So we have a very classic high pressure. Here's the 5-day average of 5-day maximum temperature. So we can see high temperatures in sort of Western Britain, maybe 29, and up into southern Scotland. And then temperatures peaked here in Estilmuir at about 28. This is the upper one's the maximum, the lower is the minimum. So what this is sort of illustrating is there's several different ways of thinking about extreme temperatures. We might think about the daily maximum, the daily minimum, the 5-daily average, or a 30-day average. All those ways of trying to characterize this phenomena. To be honest, now I think we would build relationships between these temperatures and health and then reason on that. But that's hard work. So what I'm going to focus on this. Again, these are risk ratios. So this is the ratio between the probability of this kind of event happening in 2018 versus it happening in the pre-industrial. There's two sets of models in here. One is a large ensemble run with a fairly old climate model by collaborators in Oxford, that's in blue, and in red is a state-of-the-art climate model run by collaborators at the Met Office. That has a resolution of about 60 kilometers. This model here has a resolution of about 100 kilometers. So different generations, but they kind of give us a sense of what's happening. So this is the minimum temperature. So in our sort of state-of-the-art model, we are talking about ratios somewhere between 10 and 200, so quite big amplification. While in our earlier model, I should say this is a logarithmic scale, just above 1 to just above 4. So you can see differences are quite model dependent, but generally an increase in risk or frequency. Similarly, if you look at say 5-day maximum TN5X, we can see smaller risk ratios, maybe 4 or so for my state-of-the-art model, 2 or so for the less. And then if we look at say 30 days, we have bigger uncertainties, but say a slightly more coherent signal. So that, again, same message for rainfall. Extreme temperatures have become more likely due to climate change. And actually, those increases are very large, maybe factors of 10 now at the moment. And to put this in context, we can then ask, if we go into the future, using two different sets of models. One was the set of simulations carried out for the UK Climate Impacts Programme in 2009, and then the 2018 in red. They are using different scenarios going to the future. So some of these changes are due to different choices about how the future might unravel, while and the other is a change in model, more advanced model, better models, new models that represent more things. And what they're showing is the fraction of the ensemble members, so just counting them, that exceed the threshold from that heat wave in 2018. So this is say circa 2020. Our TNX is the nighttime minimum. That probably has bigger impacts on health than the daytime maximum. So that would suggest in our UK CP18 there may be a 5% increase, 5%. So it was typically a 1 in 100. So it's a very rare event. In our UK CP, maybe it's reaching 10%. But then as we go into the future, by the world of the 2020s, that maximum temperature becomes something that's basically occurring every year. It's half of the ensembles every year. See it. And then as we look at more and more things, so if we look at 5-day minimums, so the nighttime temperatures, again, these two simulations diverge from about the 2050s. By the 2050s, that 5-day extreme from 2018 is occurring 60% of the years, so almost every year. And the 30 days, so the monthly extreme, is occurring maybe 60%. So that's essentially, so the takeaways from all of this, I think, are that climate change to date has already changed extremes. That is, they've become, for the two cases I showed, they've become more extreme and more frequent. For extreme precipitation, that change is relatively small, tens of percent. While for temperature extremes, essentially they're becoming 10 to 100 times more common. So that's the message. What should we do about it? Well, we have to do two things. We have to stop emitting carbon dioxide, and we have to prepare for these different climates. The obvious thing for Scotland to start thinking about heat waves as a potential cause of mortality amongst elderly people. I really don't want to die in my mid-70s in a heat wave. That would be very embarrassing for my family. And actually, in terms of drainage systems and things to do with extreme rainfall, we have to expect more of that. And that's all I want to say.